Welcome to section 3.2, comparing the infinite. Be sure to take notes along with me, complete the problems, pause the video often, replay it as many times as you need to make sense of what we're doing here. So this is going to be pairing up collections via one-to-one correspondence. So just because a specific attempt failed does not mean that the task at hand is impossible, and we're going to carry that through as we complete this section. So how much bigger is the set of rational numbers than the set of natural numbers? And how many fractions are there between 0 and 1? So that's what we're going to aim to answer today. So just pause the video here, think about this, jot down some notes, take some guesses, and then press play when you have some ideas and are ready to move on. So let's consider for a moment here, what is the smallest number of elements a set can have? So maybe pause the video here, consider what you think could be the smallest number. And maybe you're thinking, okay, there's a really small set, A, B, C, that could have 3. What about just 2? What about 1? What about the empty set? So these sets all have a set number of elements, or a certain number of elements, and we call those finite sets. And we have this fancy definition here, but what it's basically saying is it's a non-empty set, so there's something in there, but it's finite if there is a natural number n such that there's a one-to-one pairing between the set and this set here, 1, 2. Okay, so let's just kind of take this set of shapes. What have we got here? Maybe an X. So there is a natural number n such that there's a pairing between this set here and the set 1, 2, 3. And what's that final n natural number? 1. We can say that there's a one-to-one pairing with this set. And so as long as we can do that one-to-one pairing with 1, 2, 3, 4 all the way till we get to whatever natural number, we can say that the set is finite. So if we take a look here, we could pair this with 1, 2, 3. We could pair this with 1, 2, 3. We could pair this with 1, 2, 3. So these are all finite set examples, and 3 certainly isn't the only number of elements you could have. So what is not a finite set? Well, that is an infinite set, one that does not have a natural number n that stops it. So let's look at infinite set examples. So the first one that we're going to be talking a lot about in this chapter is the natural numbers, which starts at 1, 2, 3, 4, 5, and continues on forever. Infinite. The real numbers, that includes all the whole numbers, rational numbers, natural numbers, integers. Those are the real numbers. So that's like the square root of 3, pi, 4, -7, 1/2, 0.3. These are all real numbers. And then it doesn't have to just be math, the set of all possible poems, right? That's an infinite set. We couldn't count how many poems there are because they could keep growing. When we talk about the size of a set, we're talking about the cardinality. And so it's not the number of elements, it's the size. And the more we practice with it, the easier it'll see. But we're not actually comparing the number of elements, but the size. So two sets have the same cardinality if there is a one-to-one correspondence between the elements of one set and the elements of the other. So when we determine the size of a set, the cardinality, we're comparing it using the one-to-one tool. So if we think here, okay, the stars have a one-to-one correspondence with the states. And so we can say that they have the same cardinality because I could pair up this star with this state and this star with this state. And I can continue on forever until it stops, and I see that I have a one-to-one correspondence. So we can actually use one-to-one pairing as the tool for comparing the sizes of infinite sets. So that last example was a finite set, but we can do it for infinite sets. So let's examine this here. We've got the natural numbers 1, 2, 3, 4, 5, 6, 7, 8, and then we get a new set where we have forgotten about 1, right? We start at 2. Are both of these sets infinite? And does one set contain one less element than the natural numbers? Because I got rid of 1 here, is this set smaller? Is it smaller by 1? Are they both infinite? So I want you to pause the video here and just jot down some predictions, what you think could happen, how do these two sets compare, and then press play as we continue on. So the idea here is that basically kind of going back to the barrels from the last section, if we had like barrels of cars and oh my, that's a car, oh boy. So if I have barrels of cars and then I start with one less car, we could say, all right, then there is one less car in this barrel. So the idea is, can we say the same thing for infinite sets? Sets that go on forever. Is it one less? And then, or do we want to say, hey, this is infinity, this is infinity. Let's not compare them. Infinity's infinity. Doesn't really matter if we compare. So let's use one-to-one correspondence to make sense of this. So first, let's pair them up. So here is the new set. Remember, we forgot about 1. And here are the natural numbers. They start with 1. And if you look at this pairing, then that would say, yes, the new set is 1 less. But that's wrong. And the idea is that just because this is one pairing doesn't mean it's the only pairing. And the idea is if we can find a pairing which demonstrates one-to-one, then it is one-to-one. So now we have to get creative. Okay, how can we pair this in a different way to see if there really is one-to-one? And so the idea is, what if we kind of go back to our barrel idea? And in that barrel, if we were to take a natural number, and then we would pull out a number from our new set. And then we would pull out a natural number, and then a number from our new set, and then a natural number, and a number from our new set, and so on and so forth. And we can actually see that there is a one-to-one pairing here. And the idea is we could actually name, hey, if I were to grab a natural number 20, I could say, well, what does it correspond to in our new set? And if we look here, we see 19 goes to 20. Well, 20 is going to go to 21. And I could keep going. I could say, well, what about 41? What's that going to go to? Well, if I grab 41, that's going to go to 42. And what if I grabbed n? Well, I can see the pattern here. These are increasing by 1, so it's going to go to n plus 1. And I can say that, hey, this is a one-to-one correspondence. And I can go one step further and say that, hey, they have the same cardinality. They are the same size. So after completing this infinite process, no numbers would remain. Those barrels are going to be empty. Because every time I say a natural number, I can say another new set number that goes with it. And you'll see that correspondence that I use there is this arrow kind of back and forth. And so this correspondence means that the number n from the natural number barrel is paired with the number n plus 1 from the new set barrel forever, and that that's going to go on, and the barrels will eventually be empty if we were to do that infinitely many times. So is there a set of numbers that has a greater cardinality than the cardinality of the natural numbers? So we have the natural numbers, remember, start at 1, 2, 3, 4, 5, forever. We looked at a new set where we forgot about 1, and we saw that they were the same. So is there another set that has a greater cardinality? So pause it here and just think about it. And now that you're back, let's look at the even numbers. What do we think about the even natural numbers? How could we compare the cardinality of the evens? Well, it's the same idea. Can we do a one-to-one correspondence? And I can say, okay, these are the natural numbers. If I pull a 1, that goes to a 2. What a 2 could correspond to a 4, and a 3 could correspond to a 6, and so forth. And if I can say, all right, what about n? What would that go to? So if this is n, it corresponds to 2n. And so these happen to be the same size. Okay, what about the integers? All right, let's list out some integers. Well, if we started with the natural numbers, 1, 2, 3, 4, 5, 6, and the integers, those start at 0. And then they go to 1. And then don't forget about the negatives. That's kind of the difference here, right? We have 0 and we have negatives. And then we have 2 and -2. Now remember, we can pair in all sorts of different ways, but this is just the way that I've started here. And I guess we'll just go one more to get those negatives. So these correspond. Here's our n. So what kind of patterns do we see here? All right, so if we have n, okay, if we've got n, and actually let's kind of go this way, let's look at this. How does this correspond to this here? This is a 2. What happens with my even numbers? What happens with my even numbers? What do those correspond to? And maybe I'll even put it over here so we can kind of see, well, an even number always corresponds back to half of it, right? The 2 goes to 1, 4 goes to 2, 6 goes to 3, so it goes to half of it. And what about my odd numbers, plus 1, 2n plus 1? Those correspond to the negative versions, right? Those correspond to the negative versions of those n, right? Because the 3 corresponds to the even value, positive, but negative. The 5 corresponds to the even value 2, but negative. The 7 corresponds to the even value 3, but negative. So we can say that those have the same cardinality. And when we come back, we're going to look at the rational numbers and how that cardinality compares to the natural numbers.